Very welcome students to the lecture of Artificial Intelligence, Knowledge Representation and Reasoning. We today are going to see the depth first search, but before that I would like to what you can say conclude what we started yesterday. And we started yesterday what we call it as a breadth first search. So So what is this BFS or how actually it works? It is also called as a state space search. Okay, and this is of uninformative search. Okay, breadth first search. We are now trying to devise the algorithm for this thing. So what is say that is given a graph or what we call as a tree, given a graph of tree, but instead of saying tree, because tree is a special type of graph, okay, we can say is as a graph only, given a graph, okay. G, which combines, given a graph G which have the vertices edges, okay, which is having the set of vertices, set of edges, and the edges may have the set of weight. Okay, the given graph, this G V E W. Okay, then BFS work as below. So if you go to stage 1, okay, if you go with the stage 1, today's date is 15th September 2021. Yesterday, due to some mistake, I forgot to record our lecture. So I'm going to re-record the BFS explanation and then try uploading it on the YouTube channel TutorASRumale. Okay. So how this graph, given a graph G vertices, edges and weight, then BFS work as a follow. Okay. Select the start node or what you can say vertex V1. Let's call these as a V or VI, or maybe call, you can say it as a S VS, or you can simply say something. Okay. Select the start node vertex V. Okay. Second, explore all adjacent vertex or vertices from VS. We got this as a VS, start node as a VS. Okay, start from VS. So what we will get? Then we will have check if all adjacent vertices are visited or not. What we call as an X1, visited or not. If they are visited, okay, if all vertices are visited, update in a queue. In order of visit or in order of exploration, what we call as. We go on doing this in exploration. Fifth, move to new vertex from the set of visited vertices. From the set of visited vertices. Check for all adjacent vertices. Okay, you have to check for all adjacent vertices. Okay, from the new vertex or vertex. Then seventh stage is there. When you check all these from this new vertex, okay, if vertex adjacent is already visited, ignore it but register the path. So here you are registering this path in adjacency matrix. In adjacency matrix. Okay. So now we are on eighth stage. Okay. Explore all unvisited vertices explore all adjacent unvisited adjacent vertices. Okay. 9 is repeat. Okay. Repeat from step 3 onwards. Repeat from step 3 onwards till all the vertices in are visited. So this is your breadth first search, what you can say, textual explanation. Okay. What it uses? BFS uses Q, QUEQE, or what you can say, first in first out data structure to register visited vertices. So it uses these people, and it is a complete search of things, and it goes for all the vertices. So how it actually works, and just a little bit explanation, because today we are going to look into the DFS, that is a depth first search. Okay, so I'm just trying to give you a simple what you can say. I have to make this small, and I'm just using dark green. So here we are. So here we are having the first node is checking line. Okay. This is say suppose a given graph. You are having the node here, another node is here. Okay, another node is here. Then you are having one node here, and you are having a something like this. And all these these nodes are connected. All these nodes are connected with each other in a way that you can say that these nodes can have. I'm not drawing. I'm just trying to recreate the yesterday's graph. So we are having this graph here. So this we number as 1, this as a vertex 2, V2, this as a 3, this as 4, this as 5, this as 6, and this is 7th, or what you can say our goal node. So this is our VS or starting vertices, or simply S generally called as. This is our goal vertex. Okay. So when we are using the BFS, okay, what we generally use when we use this BFS, first this vertex 1 is selected. Okay, vertex 1 is selected. Once this vertex 1 is selected, okay, once this vertex 1 is selected, this BFS explores all the vertices which are adjacent to this vertex 1. So the vertex 1, this 2, 4 and 3, they are explored, and it maintains, okay, it actually maintains a queue. It maintains a queue here. So the first selected vertices, the queue is, that is, you are having 1. Okay, now you are exploring, so you go to the 2, 3 is explored, and 4 is explored. So once these are explored, what happens? You get no vertex which is adjacent to 1. Okay, which is adjacent to 1. So what happens? We move from the vertex 1 onward. So because there is no vertex now available which is adjacent to 1, we get, means from 1 only these 3 vertices are adjacent. For 1, these 3 vertices are adjacent, so we go from 1 to 2. Now for this 2, the scope of adjacent vertices is like this, but this 1 is already visited one, that is, you come from 1 to 2. So instead of going this, you are simply registering that path and you go to the vertex number 4. You go to the vertex number 4. So 4 is explored, and there is no more can say vertex to explore. So what happened? Now when you register this 4, you already know that 4 is already visited. It is explored from 2 to 4, but it literally won't what you can say what give any path. So you simply register that path into the adjacency matrix, because there already exists a path from 1 to 4. Alternate path is registered. After this, we go to the next vertex. Okay, and that is the all visited vertices. So which are the visited vertices? 2, 3, 4. 1, 2, 3, 4, these are visited, because for these 2 only 4 is adjacent and not visited from 2. We simply register the path and we go to the 3. We go to 3. So when we go to 3, okay, for these 3 also we are having the same exploration, that is 1 and 4. The 4 is unvisited adjacent vertex to these 3, and for it is already visited one. So the same thing get repeated here, that is from 3 you register path to 4. Okay, so now 3 is also over because there is no other vertex from 3 to any other I can say they in link to any other vertex, so we can visit the other one. So now you got the 4 one. Now here at 4, what we are having, the 4 is having the complete scope. So your 4 is having the complete scope, this much of scope, because you have 2, 3, 5 and 6, these are the adjacent vertices to 4. Okay, but 3, 2 and 1 are already visited. This is 1, 2, 3, 4, 5, 6, these are already visited. So we are simply ignoring them. Path is already registered in adjacent matrix, and you are having 4 here. So what happened? This 4 now go on exploring the unvisited vertices, that is 5 and 6 at the same time, or I could say one by one. So you visit this 5, you enter the 5, okay, and here you enter the 6. So truly unvisited vertices for the vertex 4 are 5 and 6. So you got this registered in queue now. Okay, because 2, 3, 4 were already registered way from 1, you are not registering this in queue once again. So what you get, 1, 2, 3, 4, only path is registered in adjacency matrix. Now you are having this 5 and 6, these are visited vertices. Is there any vertex remain that you can visit from 4? No. So what will happen, you will select the next vertices from these visited vertices set, because all these are already explored. So you got the next one, that is the fifth vertex we consider. Now if you consider the vertex 5, this is the scope of vertex 5. So what, this 5 can visit to 4 and 5 can visit to 7 are goal vertices. The problem is here, it is already we come from this 4 to 5, so we are ignoring it. We go for only the unvisited vertices, and unvisited vertex is 7. So we visit 7 now. We visit 7, which is the only vertex now that is possible from 5. Okay, unvisited vertex from 5 to 7, path is also registered. Now what happened, you have the visitors, the 5 is over because now there is no other vertices, so you go from 5 to 6. Now this 6 is also having the similar what we can say scope, that is it have the two vertices adjacent to it, 4 and 7, but 4 is already visited, yes, because you come from 4 to 6, 4 to 6, so you're not going to back. So unvisited vertex is only 7, and what we go from 6 to 7, but 7 is already visited from 5, so you only register the path. So this exploration happens in this way, that is 5 actually first visits this 7 and then 1. So if you go on building a graph for this, the graph will look like this, that is you are having 1 here, from 1 what you visited is 2, okay, consider this as a 3, then this as a 4. Okay, so you visited vertex 2, this is 3 and this is 4. Now you are using 2. From 2 you visited what? 3 and you visited 4 only. But if we see here, there is actually from 2 to 4 there is a path, okay, but 4 is already visited from 1, so we show this path diagrammatically using some dotted line. So these dotted line are called as cross links. In the same way you have cross links from this 3 to 4, okay, that means there exists a path from 1 to 4, direct path, and there also exists an alternate from this 3 2 and 3. Okay, so now we got here at a 4. Now for these four we visit what? The new vertex. Okay. So for these four we go on visiting 5 and 6. Okay. So here we are having the 6th number. Here we are having the 5 number. Now what happens? From these 4, when we go to this 5, okay, this 5 actually explores the 7. Actually explores the 7. Yeah. But for this 6, 7 is already visited by 5, so it becomes the alternate path, and then we show that alternate path using dash line, or what we call as a cross links. So this will be the traversal for breadth first search, and we already have seen or discussed in yesterday's lecture that breadth first search can be used to do the things in a way, or what we can say, to find out the shortest path, and likewise, and to lay down the electric circuit, to lay down the plumbing or water things, and likewise. Okay, so it is quite a versatile and a very useful algorithm which is used in a artificial intelligence to acquire the knowledge base and learning. Now, if you are on the tree, let me explain this BFS for the tree, because when it's a tree, it is quite easy. In a tree, you have generally have the root node. Below this root node, you are having the say 2 nodes. We are just creating a binary tree, and here you are having the 2 node. Okay, leaf nodes likewise. So what if you are having a tree like this, a binary tree. Okay, tree is a special type of graph where what we are having, not these nodes, leaf nodes are not connected with each other. So just like this graph, we won't get any closed circuit here. So what happen here, when you use this BFS for this root node R, okay, let's call root node as R. This is a left child, so let's call this as the LC. This is a right child, so let's call this as a RC. Okay, and these are the leaf nodes, so let's call them as L1, L2, L3. So from this R, it will visit first the L child and then the R child, and it will register them. If you give them name as a 1, 2 and 3, then 1, 2, 3 will be registered. Then it will go for this 2, and it will register 5 and 6, and then go for this 4, 3, and it will register these 2. So it's go on registering for every layer. It check. So if you number 1, 2, 3, 4, 5, 6 and 7, you get a visit like this. Okay, so now this is a breadth first search when you are using the tree. Okay, now we are going to see the depth first search. Okay, so for this I'm just erasing everything that we have created here. There is an easiest way for that. I'm saying no, and and reopening the slit. So here we are having the slit, and we are now going to see what is breadth for depth first search. Okay, so let me draw on the first the graph, same graph, but okay, we are now going to see depth first search. So here I'm going to draw both diagram first. Okay, first the tree diagram. but I will explain tree diagram afterwards. Okay, first I will explain the graph. Here you are having a tree, binary tree, simple binary tree. So you are having these elements 1, 2, 3, 4, 5, 6, 7. Yeah. So let's name them. This is 1, this is 2, or you can name them as a B, C, something like that. Okay, here you are having is 4, you are having 5. So here you are having 6 and 7. Okay, this is a simple binary tree. We are going to explain this binary tree after what you can say the graph, explanation of graph. And I'm just drawing the same graph 1, 2, okay, 3, drawing this 4, 5, 6, and our goal node, that is 7. 1 is connected to 4, 2, and 3. Then this 2 is connected to 4, 3 is connected to 4, 4 is connected with 5, 6, and these are connected with each other. So this was our graph. Okay, so just remember this, that this is the first node, this is our second node, this is third node, this is how we number them. Okay, this is the fourth node, then we are having the fifth node, then we are having sixth node, and now we are having seventh node. So now instead of doing what, the breadth first search, we are doing the depth first search. So how it start? Again the same thing is there. Now I am going to choose the different colors to show the traversal. So the first thing is that it selects randomly the start node. Let's consider the vertex 1 is selected as a start node, and it goes straight to the first adjacent node, So from 1, let's say it goes to 2. It goes to 2. Now it won't go to 3. Just like in breadth search, we are having the complete scope. So next node is not 3. So what it says, that is, as soon as it reaches to the node, first adjacent node, it goes from this first adjacent node to the first adjacent node. Okay, any that is first inquire, so it goes directly to the 4. Now here if you see, the 4 is having 1, 3, 6 and 5 as their unvisited adjacent node. Okay, so from this 4 it may go to what you can say, any visited or unvisited adjacent node. So let's consider first the success cycle. So from this 4, consider that it goes to the first adjacent node selected again randomly, that is a 5, from the set of unvisited adjacent node, that is 5. So what is here? 1, 2, 4, 5, and from this 5 it goes to the first adjacent node. Obviously unvisited adjacent node to this 5 is 7, so we reach the goal. So this is a depth first search. This is depth first search. What happened here? It goes here and it found, okay, it's reach here at the 7, but now when it goes to 7, 7 is having the adjacent node 6. Yes, so it may go down but like this, from 7 unvisited adjacent node is 6. We actually got our goal here itself, but I'm trying to complete the depth first search. Okay, so it will go to unvisited adjacent node 6. So you know that is BFS is bidirectional, DFS is not like that. So it goes to the 6, it goes to the 4. Okay, unvisited adjacent node. For these 4 you are having these 3 unvisited. Okay, you go here, from these 3 you got here to 1. Now from this one you got here to 4. This is how the depth first search go. Means depth first search visits only one node at a time. Okay? When it's a complete graph like structure. So how exactly it works when it comes to tree? Say suppose node 1 is selected, so it goes from this node 1 to node 2. From this node 2 it won't change it. Okay, there are 2 adjacent node here, leaf 1 leaf 2, so it can go either here or can go here, but let's consider it goes here. Now when it goes here, it found that there is no unvisited adjacent node available for this. So what happens? It goes and it checks whether it is a goal state or not. Whether it is a goal state or not. So it will simply go to the, it is not a goal state, it backtrack itself and visits now this. Now here also you got no adjacent node. Here also you got no adjacent unvisited nodes, so it required to backtrack. When it's backtrack, it already know that it is come from this, so it goes backtracking to node 1 and it chooses this path and select these 3, chooses this path and select 3. From these 3 it will go to this 2. Okay, and because the 7, from 7 it once again goes like and visit the 6. So if you see in depth first search, it is backtracking. Now in breadth first search, the search get complete, but in depth first search, just consider, I'm just making this path clear now from the diagram. Okay, so we are going for unsuccessful this depth first search now. Now say suppose if by mistake, if say suppose by mistake your goal set is what? 7. Yeah, you want to reach to the 7 and you using the depth first search in artificial intelligence. So it goes from 1 to 2, first selected. From 2 it's not going to check 3, it goes from 2 to 4. Okay, but now from this 4 it goes from this 4 it may go to this 3, it may go to this 3. From this 3 it may go to once again 1. Okay, and then it will go like this, it will go like this. Okay, so say suppose the situation is like this. Now simple, this is your goal state, that is you want to reach from 7 to goal state, that is 1. So from 7 it uses 5, from 5 it chooses depth first search. Okay, first link available is choose, let's say adjacent link choose. Now unvisited adjacent link is 6, for 6 unvisited adjacent link is 7 and you are stuck here, you are stuck here. So depth first search is called as incomplete search. Depth first search is called as a incomplete search. To make it complete, you need to backtrack, you need to backtrack. मतलब हम जब गाड़ी चलाते हुए कहीं जा रहे हैं, हम गलती से रास्ता भूल जाते हैं, तो व्हाट वी डू, वी जनरली टेक्स द यू टर्न. सो यू कैन कॉल डेप्थ फर्स्ट सर्च एज ए यू टर्न सर्च ऑल्सो. मतलब नाउ व्हेन इज से दैट इज वी रीच टू 7. ओके, सो विल गो, अरे हम कहाँ से रास्ता भूल गए, गलत किए. So we will consider that we actually what you can say change our path at a 4, and there was 3 or 4 outshoot there. Okay, so we'll now backtrack from 7 to 6, from 6 to 4. Okay, and now from 4 we will select the new path. Let's say we select the 3 and then we select and we go to 1. So if we find this is what you can say goal state of the thing. Okay, backtracking. Okay, so this is why it is called as a incomplete search, because if you are having the infinite depth, let's consider that is you are having node 1 universe, मतलब समझो आप जम्मू कश्मीर के श्रीनगर में हो and you want to go to Mumbai and you are using the depth first search. Okay, so what depth first search is doing, it checks the all adjacent node. Okay, no, it actually goes to the first adjacent node, and this first adjacent node is chosen randomly. It's chosen randomly. So when we say it is chosen randomly, what happens? Okay, consider from this Srinagar, you want to go to Mumbai, but you choose the Lahore. Okay, so you go from Srinagar to Lahore. In Lahore, you found it is difficult, and you are already coming from Srinagar, so you are backtracking. Okay, we are considering that from Lahore there is no link, so you are backtracking. So you once again come back to Srinagar. Now you from Srinagar you go to Shillong, Meghalaya. Okay, there you once again found no path, so you backtrack to Srinagar. Okay, you come to the Srinagar, you once again go from now Srinagar to Delhi. Okay, there are few things from Delhi to Jaipur, from Jaipur to Ahmednagar, from Ahmednagar to Mumbai, and you reach to Mumbai. So simple thing is that if you go with this depth first search, this can also be considered as a trial and error method. जब आपको कुछ पता ही नहीं होता है, at that time we try to learn things by doing or committing mistakes. Okay, so due to this special behavior of depth first search, it uses instead of queue stack as a data structure. Okay, now I'm just drawing a stack here. I'm just
Hello, sir.
yes,
Can you compare BSF and DSF side by side?
yeah, it's with graph. Okay,
Yes, sir.
yeah. So just first consider here you are having 1. Okay, 1 2 3 4 5 7 and 6. This is our goal state. This is our goal state. Let me go first with the BFS. So I'm using pink color to show the all BFS node. So what this one says, there exist three paths. There exist three paths. So it goes from 1 to 2. Okay, 1 to 4 explores this, and 1 to 3. Once these three nodes are explored, it goes on exploring these nodes. So it's for these two, it go on exploring 2 to 4. Okay, this is there. But if you see the maintenance here of the queue, I'm writing here queue of this. Okay, so first is chooser, that is our start state. From this start, you are having 2, 3, and 4 adjacent node, unvisited adjacent node. Okay, which are now visited. Now one have no adjacent node which is unvisited, so it will pass the control from one to next node in this visited list. This next node may be 2, maybe 3, maybe 4. Okay, these are selected randomly, but for our sake we are using the queue, and in a queue we are entering them in order, and that order is followed. So from 1 to 2. Okay, now from this 2, 4 is there, but you know that is 4 is already visited one, and it is visited from 1. So we say that from 1 to 2 there exists a path, from 1 to 3 there exists a path, from 1 to 4 there exists path, In the same way, from 2 to 4, there exists path. So only path get registered in adjacency matrix. Yesterday I have shown you the adjacency matrix. Okay. Now 2 is completed because now for this 2 there are only that is 1 to 2 path is there. So 2 to 4 path is also there. So you go to this visited node 3, okay, which was visited past, because this is newly visited for this core, but it is already in a list, so you are not going to do. So you go to this 3. Now 3 is having the same scope, yeah. So you know that is there exists a path from 3 to 4 also, 3 to 4 also. So this is done, this is registered, this is registered in a artificial intelligence robot. We have taken yesterday the example of car. So now car know all these paths, that is which reaches to 4, from 2, from 4 and from 3. Now from 4, once again you are having the unvisited links for to 5 to 6. So it goes to 5, explore, it's also explore or visit this 6, okay, and 5 and 6 are added in a queue. 5 and 6 are added in a queue because there is now no node which is unvisited from this 4. So now it will choose randomly the next node. It may be 5, it may be 6, but let's for convenience consider it is a 5. So it goes from 5 to 7 because 5 to 4 path is already there. So it chooses from 5 to 7. So 7 node is added in a queue. 7th node is added in a queue. Okay. So when this 7th node is added in a queue, we know that there exists path from 4 to 5, 4 to 6, and now we know that path exists from 5 to 7. But now we have to go through this 6. So again, when it comes to 6, we know there exists a path from 4 to 6, and there exists path now from 6 to 7. But 7 is already added in a queue, so you are not going to add it once again. So this is what your bread first search. So you reach from 1 to this 7 and you are registering all the paths. Now let's comes to the depth first search. I'm now using uh, green color for a depth first search. Okay. So depth first search uses stack. So first we are going to see stack. Stack, this is a when we say queue, this is first in first out data structure. When you have the stack, what we call this as a last in first out data structure. Okay, a LIFO data structure. So the one which is come last get thrown out first. Okay, so I'm once again going to change the color. Okay, color is here. So we choose now one as a start node. So one is added here. Stack one is added. From this one, it goes to randomly select the node. So from one, consider first path. It goes to 2. That is our what you can say the node goal node is 7. I am now going to stop at a goal node only, success path. So it's add 2 here. 2 is added in a LIFO. Now from this it goes to 4. It goes to 4. So it's add 4 here. You are adding in a stack. Here you are using queue, here you are using stack. 4. Now from 4 you are having this, but for we want a success node, so we are considering that it goes to 5. So it goes from 4 to 5. It goes from 4 to 5. And from 5, because unvisited node is only 7, so it goes to 7. Okay. So the artificial agent now know that a path exists from 1 to 7, but this path may not be the optimal one. जैसे हम BFS में क्या होता है, वी ट्राई टू चूज द पाथ विच इज हैविंग द मिनिमम कॉस्ट. हम सब रजिस्टर्ड कर लेते हैं एंड देन वी चूज द पाथ वंस. ओके, द फर्स्ट टाइम ओनली वी actually the robot goes in a thing. But here what happened, this is a LIFO structure. So now if I want to come back, okay, even if there exists some we can say small path, we won't go through that. Instead we go on back doing the backtracking. So say suppose now here my goal is this node 3. Just consider this. Instead of 7 my goal node is 3. अगर ये BFS है तो मैं 3 पे बहुत जल्दी पहुंच जाऊंगा. But it is a depth first search. What happened at 7, okay, I found this 6 here, but just consider that there exists no link of this 7 to 6. Just imagine, ये ग्राफ में ये लिंक ही नहीं है. So what will happen, it will pop the 7 from this stack, then it will pop the 5 from this stack, it will pop the 4 from this stack, because there is no link exist from 6 to 7. So it will go like this and then it will at 4. Okay, at 4 it will see it will pop this and it will go on doing that. Then we can visit 1, 2, and our goal node is 3. So 3. So the cost of path or a traversal is more in depth first search because it has the backtracking. Okay, and if you are having the infinite number of nodes, मतलब ये ग्राफ जो है ना, यहाँ पर मैं इसके लिए ग्राफ बनाता हूँ, एक सिंपल ग्राफ बनाते हैं ग्रीन में. ओके, which is having something like this. We are having graph. Instead of that, just consider this graph here and connectivity. So there is no connectivity considered. There is no connectivity in 6 and 7. In this case, even if you go with a breadth first search, what happened? In breadth first search, I am using blue ink now. Okay, it will visit and mark this in a queue. Now it will visit and mark this path also in queue. Okay, it will visit this and will mark this path in a queue. Now it will visit this and will mark this path in a queue. Now it will visit and mark this path in queue. So you can reach goal state very easily. Okay, goal state easily. Now just consider that our goal state is 3. That is, we want to reach from this node 1 to node 3 very easy in BFS. But now if we select the DFS instead, DFS, I am using red ink now here to explain the DFS. So DFS will randomly select just like BFS the node for traversal. So here you are going what this, you go to this node, just consider node number 2. From node number 2 you go to node number say this 4. From node number 4 you go to node number 6. Just see what happens. So from this 6 there are no nodes available. So what you will do, you will return back. So now consider if the weight of this path is 3. Okay, this backtracking causes you 3 means you are returning back. So what happened, you are registered 1 first here, 2, okay, then you are registering this 4 because our goal state is 3, then we registered 6, but after this 6 there is no path, so you have to remove this 6 now from your knowledge base. Okay, and you have to return back to this node 4. Now on this node 4, what happened? You find there are 1, 2 and 3 paths are there which are unvisited. So there are 3 nodes are there which are unvisited. So let's consider that you randomly choose. So you are chosen this node. Okay. So for this node, unvisited is here. So you come here. So you choose from this 4, you choose what? The 5, and from 5 you choose 7. When you come to this 7, when you come to this 7th node, what you find that there are no node to visit and there is no goal node available. Now what happens? You go to 5. So what you are doing? You are discarding the 7 now. You go to 5. Now from 5 you are going to once again to the 4. You are going once again to the 4. So you are discarding the 5 also. So now you are once again at the stage 4. Now for 4 you are having 1 and 2 unexplored thing. Now consider that you gone to this 1. Gone to this 1 from the 4. So 1 is here which is unvisited from 4, because 1 visited to 2 visited 4, from 4 1 is unvisited. So you are having this 1, and when you for to visit this one, now you need to pop this to last in first out thing. So you have to completely build a new what you can say is thing. Now you go one from 1 to 3 and likewise. So you reach to the goal node after a very what you can say big trouble. So it is a sometime what we call as a trial error method, an error method like something depth first search, and it is also called as an incomplete search, because if you are having the n number of nodes and if the nodes are what you can say isolated okay, BFS is also in that problem if nodes are isolated, but if there are a little bit of what you can say connectivity between nodes, and for example this node and this node they have no direct connectivity, in that case depth first search will cause the problem. So depth first search won't create the good what you can say or efficient adjacency matrix or all pair shortest path for searching the objects and likewise. But still depth first search even it is a brute force, it is very useful. Means just consider that you are using the BFS, you want to go from Pune to Aurangabad. Okay, so what BFS will do, the agent will do, that is it will recall everything and it can go things. But because in this recalling last first in first out is there. Okay, so whatever comes in first will remain there, because you won't require to kick it out to register. You have 2 3 4 5 6 7, your memory is complete. Okay, so when you delete this one, at that time only you know that there is something missing, but then again you can go for the breadth and you can complete it. That's why it is called as a complete search, or it create the complete knowledge base. It shows you the complete interlink between all the nodes in a graph, while depth first search won't show the complete interlink, because at the end when depth first search is completed you only get the stack of stack which is having the node or path. For example, let's consider with a depth first search on this tree. Okay, so from this is say suppose your start node, and consider this is as your goal node. So it goes from 1 to 2, from 2 to 4. Now it says that is from 4 there is no node to visit, so it's track back to this 2. From 2 it goes to this 5. From 5 also there is no node to visit, so it's track back to 2. Then it's track back to 1. So if you see the stack which was this first, This first stack is having element 1, second stack is having element 1 and 2, second stack is having element 1 and 2, third stack is having the entry you are having 4 here. But now in form 4 there is no node to visit, so what it will do, it will delete or pop the 4. And so when it delete and pop the 4, it will now go to 2, and from 2 it visit the next node, and that node is 6, that node is 6. But when it visit the 6, it once again find that there is no node to visit from the 6, so it will simply pop the node 6. So your stack is 1 and 2 only. Now from this it goes to 1, from this it goes to 1. So when it goes to 1, it know that there is no node 2 required, no node 2 is required. That is what we call a stack. So from this one now it goes to 3. So the new node which is registered in a stack, last in first out, is 3, is 3. Now for these 3, it know that there are things to visit, so consider that you choose the node 6. So it say that is okay, there is a node 6 that you can visit from 3, but now node 6 there is no node to visit, so you once again pop the node 6 and you backtrack, you go to the node 3, and then you go to this node 7, then you go to the node 7, you add this node 7 only, and your stack is completed, your path is registered, your path is registered. Okay, so this is DFS, depth first search. So how many nodes are actually now known or stored in your knowledge base? Out of all the nodes, only 3 nodes in this, if you go with that path. But when you use the FIFO, this first in first out something, you won't need to can say pop that first, because that is the elemental thing. So if you have the queue sufficiently large, if you have the queue sufficiently large, then you can have all the memory in your what you can say using breadth first search. That's why it's called as a complete search. You got this? Hello?
Yes, sir.
Okay. Any
Sir, but
questions? Yes.
next time
Hmm.
in that tree, it will
Hmm?
be there for all the path or 137 only.
No, no, this is a one possibility. Actually, when we go with the depth first search, there are n number of possibility. Let me use the blue ink to show you the new possibility. Consider your start node is 1. Our start node is what? 1. Yes. So that is the last in, first out. So you push this one into the stack. Now your goal node is 7. But okay, this time what you choose is the 2. First, what we choose is 2. Now consider that instead of choosing 2, it choose this. It choose this 3. It it is here directly, it is here directly, and luckily it directly goes to goal node. So you got the answer, so you got the answer. So if you go with this tree, if you go with this tree then can be considered as the possibility of paths. Just consider here, I am now drawing the depth first state space tree. Okay, this called as a state space search tree. Okay, so you are having a possibility, that is you are having the success rate, you are having the success rate. So you may get a solution. So you first visited this node 2, then you visited node 3, then you backtrack. So and likewise, so yeah, this tree is just a minute. So here you get what, the 3 7, you will get here. And so what you get, the solution set, complete solution set. Okay, so if you are having n number of nodes, we are just considering here the binary search now, but if you are having the n number of nodes, okay, then we can have the different thing. So if you go with this state-based tree, okay, if you select the first, what it have, the knowledge, that is if you go through this path, but it this unmemorizing, so it simply says that is okay, using this path you won't reach to the goal state. So this is simply pop out, means it is cut down from your knowledge base. Now you are having only this, so now whenever you want to go to this, okay, this is what you get 137. But again you can go like this, that is this is by luck, it can a chance that is you go straight and your goal state is here. But if say suppose you go like this and for depth you select this, then you require to backtrack once again. When you go on backtracking, your path is now not straight one. So if you consider this path, so what combinations we can get? First you get like this 1 2 4, then you are having this 5, okay, then you are having 3. If you go with the queue structure, then you are saying okay, there is a 7, okay, this is one possibility. Then you are having 1 2 4 5, okay, 3 6 and 7. This is the another possibility of your entire journey. Then here you are having the possibility is 1 2 5 4 3 7. This is a possibility. So what you get, the paths 1, then once again that is 2, you are visiting node 5th, you are backtracking to node 4, you are backtracking to node 3, you are back, okay, and here you go to the 6, and then you are going to the 7. So okay, and your path is only, because we are considering our goal node as 7 here, then your path is this 1 3 and 7, 1 3 and 7. Now just consider that you are having a tree where at this juncture you are having k number of nodes, k number of nodes. These k number of nodes are the nodes which consider k is 1 crore. Just consider k equal to 1 crore. Okay, and you are in BFS and your goal state is 7. Which is more efficient, BFS or DFS? Hello? BFS is more efficient because BFS registered the knowledge completely. And even if, say, suppose your queue is having only size of 100, still FIFO maintain the knowledge of all 100 nodes which are in the scope. Means अगर वो 4 पर है, okay, so it know all the paths which are going from these 4 onwards, and it also know the weightage of those paths. So what happen, generally when it comes to BFS it is called as a complete search, and when it comes to DFS it is called as incomplete search. Both are uninformed search, both are used to create the knowledge base. Now both are used for learning. Now what is this DFS की हम अंग्रेजी में बोलते हैं ना, प्रैक्टिस मेक्स मैन परफेक्ट. Okay, so DFS is like that, practice makes man perfect. So you come to know that is if you want to go to 3 or you want to go to 7, this is the path. So next time the robot not do any error. If you ask the robot to do that particular task, it will automatically follow the process, because that process is only registered. But this process, for example, just consider when you learn the swimming, what happens? आपने तैरना सीख लिया है, 1 साल के बाद पानी में उतरे, और व्हाट विल हैपन? You will swim or not? Hello?
Yes.
You will
Yes,
swim.
sir.
Why? Because the swimming memory is stored in a stack directly in your body. Okay? You will swim because it is, you will not go here and there, you will swim. You will automatically do the same thing, cycling and other things, that learning. Okay? What we call as the complete this is our DFS. But let's say suppose you are learning the words A to Z, okay, and you want A to Z words, A, B, C, D, all alphabets are known to you, and I ask you to write a story, और कंप्यूटर की एक लैंग्वेज आपको पता है, पाइथन और सी प्लस प्लस, एंड आई आस्क यू टू राइट अ प्रोग्राम. The learning now shifts from automated learning to thinking. So BFS actually enables artificial thinking. क्या करता है BFS? Actually try to see all the aspects. So if you want to build something which is nearer to more artificial intelligence, then you can use the FIFO structure and BFS. But when you want to have an autonomous system जो सिर्फ उतना ही कर सकती है जितना उसको करना है, then you go for using the DFS for the learning system. You are getting this? Okay. We already have passed the time, around it's 1:51, and I'm really thankful to you guys for actually asking questions. You know, when student ask questions, we get more inspiration to teach them in more depth and more detail. I literally got a satisfaction of teaching after many years, because it was that students usually used to ask the questions when I was in 2000 and 2003. After 2004, I found very less students asking questions. Now, this is the first time I really got this. And when you ask the questions, it becomes what you can say inspiration to us to I can say learn more, so that we can deliver more accurate lecture, more accurate information or knowledge to you. Now, yesterday I have shared on your classroom this AI Age of AI series, which was published 1 year before on YouTube Originals. There are total 8 episodes of that. So what I expect that you all will go through that. You will try to can say mug up whatever the knowledge that you will get from that series, and then we'll create a question set on that, and that will be our TAE1. Okay. So thank you very much for listening to me and giving your precious time to the subject AIKR. Thanks.